Hello everyone. In this video, I would like to talk a little bit about precision and accuracy as it relates to mathematics. In particular, I'm going to cover a concept which is called an iterative error, especially as it relates to the conversion of fractions and irrational numbers to non-terminating decimals. Video number 16, Converting Fractions and Decimals, may be useful if you want to brush up on some of these concepts. Suppose I went to visit a friend at her house one day. I'm in the living room, and my friend asks me how far away my house is. I say 3 miles. I walk with my friend out to her patio, and she turns to me and asks, "Now how far away is your house?" This is a pretty weird conversation, right? This is, of course, because when I said that I lived 3 miles away, I didn't mean that I lived exactly 3 miles away. What I meant is that I lived approximately 3 miles away. Therefore, the change in our location, the relatively few feet from the living room to the patio, is not going to change my answer. In this type of casual conversation, my answer means that, in my estimation, I live closer to 3 miles away than either 2 miles away or 4 miles away. Mathematically, we can say that I live somewhere between 2.5 to 3.5 miles away. We would equivalently say that my estimate is intended to be within 1/2 of a mile of the actual value. Sometimes we use the terminology 3 miles plus or minus 1/2 a mile. This is how we would express that terminology mathematically. Precision and accuracy are associated with things that we measure, like physical distance, weight, or time. Theoretically, anything measured has an exact value. The problem is that whatever process we use to measure that physical distance, weight, or time has some inherent level of error associated with it. Therefore, we can never determine the exact value of anything that we measure. What we can do, though, is to use increasingly careful and sophisticated methods of measurement, which reduce the magnitude, that is, the size, of any errors. When we do this, our measurement gets closer and closer to the theoretical exact value. As we reduce the magnitude of errors in our measurement, we are said to be increasing our precision. That is, our measurements are said to be more precise. We sometimes talk about a margin of error in our measurements. Let's talk about this for a moment as a way of leading into a discussion of the term accurate. Suppose I really took my friend's question seriously, so the next time I walked to her house, I used the odometer of my fitness watch to measure the distance. This is a perfectly reasonable way to estimate the distance, but there are errors. My fitness watch counts my steps based on sensing my body's motion, and so steps are not always properly counted. It measures distance based on the length of each step which I program into the watch, but my steps aren't always the same length each time. Distance is measured in a straight line, but I didn't walk a perfectly straight line. All things considered, the method of measurement I chose was a good one, but it wasn't perfect. I can rather laboriously go through each of the potential sources of error, evaluate them, and add them together to give me the biggest possible error for that method of measurement. Suppose my fitness watch said I traveled 3.2 miles from my house to my friend's house, and I calculated that the largest possible error for my method of measurement was 1/4 of a mile, which I can also write as 0.25 miles. 1/4 mile, then, is said to be the margin of error. It means that the actual distance between our two houses was somewhere between 3.2 miles minus 0.25 miles and 3.2 miles plus 0.25 miles. That is, between 2.95 miles and 3.45 miles. The Merriam-Webster dictionary defines accurate as being free from error, especially as a result of care, or conforming exactly to truth or to a standard. It is derived from the Latin meaning to be prepared with care and meticulousness. A measurement is said to be accurate if it is carefully done and within the margin of error. It is said to be inaccurate if it is outside of the margin of error. To be accurate means to obtain as close to the true value of a measurement as is possible given our method of measurement. Thus, the accuracy of my measurement is related to the precision of my measurement, which is, in turn, related to the method used in making the measurement. Suppose I wanted an even more precise method of measurement. If I used a more precise method of measurement, I could obtain a more accurate result, that is, a measurement closer to the exact value. I could use GPS positioning. In my lifetime, this went from being a pipe dream to being commonly available to almost anyone. GPS accuracy is based on a number of factors, but it is not uncommon for a GPS app on my tablet or phone to give me my position with a margin of error of 25 feet or less. Thus, if I took a GPS position at my house and another at my friend's house, the largest total error would be 50 feet, that is 25 feet at each location. My margin of error is substantially smaller using this method as opposed to my fitness watch odometer measurement. Therefore, the resultant measurement is much more precise. In this case, a careful measurement would give me an accuracy to within 1/100th of a mile, that is 50 feet. Suppose I did this and my measurement using GPS was 3.26 miles, plus or minus 0.01 miles. Remember that I said that accuracy and precision are always related to one another. When I used my fitness watch, the precision was plus or minus 1/4 of a mile, and my measurement of 3.2 miles was accurate. Using GPS with a margin of error of plus or minus 1/100th of a mile and a measurement of 3.26 miles, my original answer of 3.2 miles is no longer accurate. As my method of measurement becomes more precise, the tolerance for accurate readings becomes smaller. We usually imply precision and accuracy by how we represent decimals. When I told my friend that I lived 3 miles away from her, that means that I lived closer to 3 miles away rather than either 2 miles or 4 miles. If I had told her that I lived 3.0 miles away, then that implies that my answer is accurate to the nearest 1/10th of a mile. That is, I live closer to 3.0 miles than either 2.9 miles or 3.1 miles. The precision of my answer would be 3 miles plus or minus 0.05 miles. If I would have said that I lived 3.00 miles away, that would imply an accuracy to the nearest 1/100th of a mile. When expressing a decimal that represents a measurement, be careful not to add or omit places to the right of the decimal point. That would imply a level of precision of measurement which is not true. When applying arithmetic to areas like engineering or construction, the measurements of 3, 3.0, and 3.00 are not equal to each other because each number implies a different level of precision. These same principles of precision and accuracy occur when we deal with repeating decimals and decimal expressions of irrational numbers. Let's take the fraction of 1/6 expressed as a decimal, for example. It is a repeating decimal, meaning that it repeats infinitely. I can represent any repeating decimal precisely with a line over that portion of the decimal which repeats. In this case, it is the 6. The problem is that in order to use this decimal in practical applications, we need to round it off at some point. By rounding it off, I mean that we must express the decimal as some finite number of places to the right of the decimal point, and then express it as the decimal closest to that value. Suppose I wanted to express the fraction 1/6 as a decimal to the nearest 1,000th, that is, 3 decimal places. The first 3 decimal places of the fraction 1/6 are 0.166. Since the 4th decimal place is a 6, I would round the 3rd decimal place up to a 7. It is the nearest decimal to 1/6 to the 1,000th place that I can write. But it is not exact. In rounding the decimal to the nearest 1,000th, I have introduced a small difference. I can calculate the difference. Here it is. There is nothing inherently wrong with the process of rounding. I really don't have any choice if I want to work with a repeating decimal or an irrational number expressed as a decimal. It becomes a potential problem, though, if I round the repeating decimal or irrational number off, and then use it in mathematical operations. Suppose I wanted to calculate the distance a TV satellite must travel in 24 hours. TV satellites are the ones that provide us with our favorite TV shows by transmitting the TV signal from space down to our dish receivers. A crucial aspect of a TV satellite is that it is geostationary. That means that it stays in its same position relative to the Earth. Our dish receivers must be pointed very precisely to the position of the satellite. If the satellite is not geostationary, that is, if the satellite moves relative to us, Then we would have to periodically adjust the position of our dish receivers in order to receive the TV signals. It would make receiving the TV signals much more complicated and would probably take away much of the enjoyment of watching Seinfeld reruns. For this calculation, let's assume the TV satellite is orbiting the Earth at 35,786 kilometers above Earth at the equator. This is a typical geostationary orbit. First, I find some basic information on the internet. NASA has some useful information. I learned that the Earth is not a perfect sphere, but it is quite close. The radius of the Earth at the equator is 6,378 kilometers, and the satellite height above Earth is measured relative to the equator, so this is a good value to use. Being in geostationary orbit means it takes 24 hours to make one orbit, the same as the Earth's rotation. That's all the information I need. Now I need to do a little math. The TV satellite goes in a circular orbit with the center of the orbit at the center of the Earth. So the radius of the circular orbit would be the sum of the radius of the Earth and the distance the satellite is above the surface of the Earth. That total is 42,164 kilometers. The distance of one complete trip around the Earth for the satellite would be the circumference of the circular orbit. Here is the equation for calculating the circumference of a circle with a known radius. It is twice the radius times the irrational number pi. But I don't like irrational numbers. They make me uncomfortable. So one of the first things I decide to do is convert pi to a decimal. Remember that, as an irrational number, the decimal representation of pi will never terminate or repeat. However, pi has been calculated very, very precisely to over 30 trillion decimal places, as a matter of fact. Here is pi expressed to the first 10 decimal places. I want my answer to be accurate to the nearest kilometer, so I figure that using pi as equal to 3.1 is fine. Here's my equation with the decimal 3.1 for pi, and the radius of orbit of 42,164 kilometers. The total distance is 261,416.8 kilometers, which I round to the nearest whole number of 261,417 kilometers. No problem, right? Well, yes, there is a problem. When I estimated pi as 3.1, I created a tiny difference between my estimate and what the actual value of pi is. The problem is that I then multiplied that tiny difference by 84,328, twice the radius of orbit. Now my tiny difference isn't so tiny anymore. The term iterative means to repeat something. An iterative error occurs when I perform a process which accumulates errors. In this case, the error is the difference between the actual value of pi and the estimate of 3.1 that I used. I created a rather large error when I multiplied that tiny difference by 84,328. If I had used pi as 3.14159 instead of 3.1, then the distance would be 264,924 kilometers, a difference of 3,507 kilometers. To put 3,507 kilometers in perspective, it is a little more than the straight line distance between Phoenix, Arizona and New York City. How much difference does it make? It depends on how important it is to be as accurate as possible. In our hypothetical scenario, if the satellite were 3,507 kilometers short of being in perfect geostationary orbit each day, then we would have to reposition our TV dish about twice a day in order to receive the TV signals. So much for Seinfeld. At least you would probably get to know your local TV technician quite well. The simplest solution for avoiding this type of iterative error is to refrain from converting a fraction into a repeating decimal and to leave irrational numbers like pi in their irrational form. If I would have simply told you that the orbit of our hypothetical TV satellite covered a distance of 84,328 times pi kilometers per day, then this might not be as intuitive as you like, but it gives you the opportunity to determine the degree of precision that you need based on how you intend to use the data. That's all we have for this video. We only have one more topic in arithmetic to cover, and that is to take a closer look at exponents and some of the rules for working with exponents. Thank you, everyone. Have a great day.
We hope to see you at Veterans Upward Bound very soon, and recommend a friend.